This is another video in my series on alternating current. In this video, I'm going to work on an alternating current circuit example using real numbers. You will find this topic, along with others, in my course entitled Basic Fundamentals of AC Circuit Analysis. You can access this and my other courses on my Stan Store at this web address. Here is an example of a series RLC circuit. We can now determine the equivalent impedance of the circuit. The first step is to determine the reactance in ohms for the inductor, which is given by 2 pi times the frequency of the circuit and L times L, which is the inductance of the inductor. Substituting actual values, we get 2 times pi times 60 hertz times 650 millihenries, which works out to 245.04 ohms. For the capacitor, its reactance is given by 1 over 2 pi times the frequency times the capacitance in farads. Substituting actual values, we get 1 over 2 times pi times 60 hertz times 1.5 microfarads, which works out to 1.7684 k ohms. The next step is to express all the reactances and resistances in mathematical terms. The impedance of the resistor is easy. It's still regarded as purely real impedance, and it has a polar angle of 0 degrees. The impedance of the inductor is the inductive reactance translated into positive imaginary impedance, or an impedance at plus 90 degrees. And the impedance of the capacitor translates into negative imaginary impedance at minus 90 or 270 degrees. These impedances could also be translated into polar notation. For the resistor, it is 250 ohms at 0 degrees. For the inductor, it is 245.04 ohms at 90 degrees, and for the capacitor, it will be 1.7684 k ohms at 270 degrees or minus 90 degrees. Now, with all the quantities of opposition to the electric current expressed in complex number format, they can be handled the same way as we handle plain resistances in a series DC circuit. We can draw up an analysis table for this circuit and insert all the given figures: total voltage and the impedances of the resistors, inductors, capacitors. Unless otherwise specified, the source voltage will be our reference for phase shift, and so will be written at an angle of 0 degrees. Remember that there is no such thing as an absolute angle of phase shift for a voltage or current, since it's always a quantity relative to another waveform. Phase angles for impedances, however, like those of resistors, inductors, and capacitors, are known absolutely, because the phase relationship between voltage and current at each component are absolutely defined. Notice that we are assuming a perfectly reactive inductor and capacitor with impedances phase angles of exactly plus 90 and minus 90 degrees respectively. Although real components won't be perfect in this regard, they should be fairly close. For simplicity, we'll assume perfectly reactive inductors and capacitors from now on in my example calculations, except where noted otherwise. Since the above example circuit is a series circuit, we know that the total circuit impedance is equal to the sum of the individuals. So the total impedance is going to be given by the sum of the resistance impedance, the inductor impedance, and the capacitor impedance. So in terms of numbers, that's 250 plus J 245.04 minus J 1.7684 K ohms. Doing the math for those numbers, the total impedance is written in rectangular form: 250 ohms minus J 1.5233 K ohms, or 1.5437 K ohms at minus 80.680 degrees. We can now plug that into our chart. We can now apply Ohm's law. I is equal to E over Z in a total column to find the total current in this series circuit. Now the M designates milliamps since the impedance was in K ohms. Now, being a series circuit, current must be equal through all components. Thus, we can take the figure obtained for the total current and distribute it to each of the other columns. Now, we were prepared to apply Ohm's law again, this time solving for the voltage drop across the individual impedances. We use E is equal to I times Z. And we can fill in across the top of the table for the voltage drop across the resistor, across the inductor, and across the capacitor. So we have successfully used Ohm's law and complex numbers or phasors and impedances to calculate and solve for the current and the voltage drops in a series RLC circuit. Notice something strange here, though. Although our supply voltage is only 120 volts, the voltage across the capacitor is 137.46 volts. So how can this be? Well, the answer lies in the fact that when you connect impedances up, and those impedances include capacitor inductance, there is a resonant frequency that will allow the voltages to essentially ring back and forth, building and discharging, to mount to a voltage level that's, in this case, 137.46. Now, the theory and the way this happens is the subject of another lesson. However, you don't have to worry about it if all you're wanting to do is calculate the voltage drops and the currents. The math looks after that for you. This video is part of my Electrical Technical Information series. It is this series that I'll be covering essential topics to help you understand electrical systems. Be sure and stay tuned, as I'll also, from time to time, be reviewing electrical products that, in my opinion, are worthy of paying attention to. This address will give you access to the supplier of aforementioned products, and it is also a connection to obtain a free copy of my 50-page electrical power crib sheets, which will serve as a quick reference of technical calculations that you may need. Also, by providing me with your name and email address, I will be able to forward you information to connect
with electrical products and to provide you with notifications of more electrical training in future videos. Of course, this website is case sensitive. I'll spell it out for you so that you won't make a mistake. The first part of it is all lowercase https:// bit.ly/3, then uppercase V, uppercase J, lowercase l, lowercase e, 8, lowercase z. One of the vendors worth taking a look at is Anchor, which produces a full range of mobile and stationary power supplies. To have a look at their full range of products, simply go to this website, lowercase https:// bit.ly/3 lowercase z, 3 lowercase b, lowercase g, uppercase G, lowercase a. At this website, you'll be introduced to Anchor's full range of products, from the very small to the very large.